All right. A lot of vocabulary to talk about. A lot of vocabulary. So, you might choose to, I mean, yeah, you probably should write this down. But you can always, I'm going to give you very condensed and informal definitions. You can probably condense them even further. So, what is a statistic? At its most fundamental, a statistic is some kind of summary. And it's usually a numerical summary. I record all these and post them online on our Canvas page, so there's that too, if something. Do you need a refresher? A statistic is a numerical summary. So you already know some statistics, but the average. We all have a, I have whatever my height is, and you have your height. And I could take our average height, and somehow it summarizes the behavior of the heights in the people in this room. Right? You have the idea of variable. This is much different than, it's similar to, but very different from what you would think about a variable in, let's say, algebra. It's similar in that it can be thought of as a placeholder for this other number. Like, so in algebra you had, x plus 1 equals y. And we could, the x was just a placeholder. You could think of it as a placeholder, and you could take another number and stick it in there and then compute y. But we're not going to do any computing with these statistical variables. They are a variable is a description of the type of data you are collecting, right? So in the height example I just gave you, height would be a variable. Height is a variable, and there's 4 different possibilities for what that variable could take on for the people in this room, right? A variable is a description of the I'll just say description of the data. It's probably not the best way to say it, because I'm not really describing the data, I'm describing what each of those data points are, right? If I gave you the numbers 66, 61, 72, 73, they could be ages, but what if my variable was heights? Well then, okay, now you know that they're heights. It must be in inches too, or else if it was centimeters, they'd be really short. So a variable is like a description of the data, let's say, in your sample. But then there's this word sample. What does that mean? We have 2, so this definition begs, there's 2 other words here that, what do they mean? Sample and data. before you can talk about either of those, you need to know about population. As a statistical researcher, the researcher defines what they want their population to be. The researcher defines the population. If I'm doing research on a medication to lower cholesterol, then there's a natural population that's associated with that study. It would be people with high cholesterol. I'm not going to give people with normal cholesterol my cholesterol medication, right? So my population would be restricted down from the collection of all people to just those with high cholesterol. Or my population could be, it can literally be anything I define it to be. If I want to study retention rates at West Coast University, then clearly my population would be students at West Coast University. Can't be students at some other school because that wouldn't be relevant. And I wouldn't want to have my population be anything smaller than all of the students at West Coast University. So it's like you can restrict your population to be something very specific, but then all of a sudden it needs to be as big as possible, right? So if I wanted to study retention at West Coast, I would not just look at people in nursing corps already. I would need to look at everyone, and not just this campus, but all 5 of them. Populations are usually very large. They're usually very large. And a sample is just a sub-collection from the population.
So it's kind of just like a smaller population within the population, basically.
Exactly, but we will call it sample. Mm-hmm. So the population, if it was West Coast University students, and I'm studying retention, then I might construct a sample by randomly choosing one student from each class. Okay? So somebody would come in here, they'd pick one of you, and that person would go into the sample. And so the sample becomes much smaller than the population, right? And the place where statisticians do their work is on the sample. In most cases, in nearly every case, the population is too big to study properly. Like go back to the example of cholesterol, right? There would be hundreds of millions of people worldwide, at least, if not considerably more, into the billions of people with cholesterol. Let's just say there's a billion, okay, worldwide. And because I'm going to offer my medication for sale anywhere in the world, so my population would need to be all the humans. In fact, your population would not even be limited to the humans currently on Earth. It would be all the ones that would be born in the future as well. So all of a sudden, the population becomes something you can't even study because some of those people aren't even here yet. That's where the power of the sample comes in. If the sample is of sufficient size and we collect it in a satisfactory way, then we can study this sample and understand something about the population. We can extend the results of the sample to be a fact about the population. That's the power. And then the data is obviously or maybe it's not obvious, but it is the collection of measurements of your sample. A collection of measurements for a particular variable for your sample. So the difficulty with all of these vocabulary words is how they nest together like this, right? Where they're all kind of circular. I mean, data here is talking about, it's got variable and it's got sample, but then variable referred back to data. You know what I mean? So it's like you need to know all three of them, and simultaneously, they're not independent of one another, right?
So you take the data from the sample.
I can form a data set by going and measuring a particular variable on my sample.
Okay. But so you're not necessarily going to get data collection from the population because it's going to be too big.
If I were to do that, that has a particular name. It's called census.
Census. So that's more. Would that secondly just be more of like a generalized kind of conclusion then? If you took the data from a population then?
So if I can access my whole population and poll everyone in the population, right? Then I wouldn't. Then the summary I would get is not a statistic. It's called a parameter.
Okay.
But it's the same thing, right? If I had the average, if somehow I could visit every American and say, I need to know your blood pressure, and then find the average blood pressure of all the Americans, that would be a parameter. Okay? I can never do that. It would be way too hard. How do I know I didn't miss someone? Furthermore, how do you overcome that issue with the population would necessarily have to say all of the Americans that are alive right now for which I can find, right? And then suddenly that's not really the same thing as the population of all the Americans. I'm sure, how many people are pregnant in this country right now? I can't measure those babies' blood pressure, I don't think. Can I do that?
Pretty sure.
So, pretty sure they can. Maybe when they're older.
I don't
know. So
they can do heart rate.
Yeah.
For a fact. I'm pretty sure.
Yeah,
Honestly,
they can.
Now they can. There's surgeries they do now with babies where they can cut the mom open, take the baby out in the amniotic sac. It's still like not born yet.
Yeah.
Do a procedure and put it back.
Yeah. Oh, yeah.
There's only like 2 or 3 doctors in the whole world that can do it, but like it can be done.
It can be done. But
So
I'm not going to be able to slip a cuff from that baby's arm. Okay, so anything that would have to be done there would be, and plus, I wouldn't even know what to really do with that information. Why should a baby's blood pressure be at all the same as an adult's? I really don't know. So it becomes very difficult to try and learn something about a population. But if you could, if it was something simple, average salary of adults in America, well then I would learn a parameter, not a statistic, and it wouldn't be a the sampling technique that you're using there is called a census, where you just check everyone. We're going to talk about the different sampling techniques to all the different ways, or the main different ways that I can collect a sample from my population such that these ways are reliable, trustworthy. And the data, you can form a data set that is about your entire population, or you can form a data set that is just about your sample. Either way, a data set is just a collection of numbers or objects, right? And anytime we're talking about like if I wanted to discuss the average population, if I wanted to discuss the average salary of the population, I would use a different symbol than if I was talking about the average salary of my sample. Okay? And so we're going to have different symbology for each of the population and the sample. Now, variables come in two distinct varieties. You have discrete variables and you have continuous variables. It's at this stage of where students first encounter their taste of confusion in statistics. Because sometimes it can be difficult to discern between the two. This is not discrete like they're private or something. It's discrete as in a synonym for this would be countable. In fact, if you see discrete, you should instantly just replace that word with countable. Because we have an intuition about what something should mean if it's countable. This is a formal mathematical word. It has a formal definition. It just means that I can take that collection of objects and assign each one of them an integer, right? So there's a discrete, the variable of height in this room, the variable of just a number of people in a particular room on campus is always going to be countable, because I could just go into the room and I could count up 1, 2, 3, 4. I could go to each room on campus and count up the number of people in there, right? There's never going to be this situation where I walk into the room and there's so many people that I run out of numbers, right? I will always, even if there was an infinite number of people in the room, I would never run out of numbers. I would go to the next one. If this is countable, then that one must be uncountable.
Like an unborn baby?
No, actually not. Because that's an interesting take, because it's like, where are they at? I don't know. But no, I could still assign that baby a number, right? They're countable. Let's talk about some examples of things that are countable. Very obviously, finite collections are countable, because if there was only 4 people in the room, then I didn't run out of integers to assign them. So every finite collection must be countable. The number of stars in the Milky Way galaxy is finite. You can count them all. There's a bunch, but it's certainly finite. The number of molecules that the sun is composed of is finite. It's mind-bendingly large, but it is countable. It is not even infinite. So collections can be very, very large and still be finite. Even all of the stars in the observable universe is countable. So you may be thinking, well, gee whiz, when can we ever have something that's uncountable, or even something that surpasses finite and becomes infinite? Well, Countable. I could pull them out one at a time. What about the collection of all the fractions? It's countable. How could you demonstrate that?
They're fractions and statistics.
Yeah.
What?
Oh
They're
yeah.
numbers.
They are numbers. But numbers like pi are numbers. There's lots of so it's all about developing like a little strategy, right? Because what does it mean to be countable? It means we assign each one of them an integer. Integers are 1, 2, 3, 4, 5, and so on. So what you do is you say, well, I'm going to have right here in the middle the most basic fraction of all, 0 over 1. Vertically, I will let the denominator change, right? All of these are still the number 0, by the way. But the denominator is changing in each one of them. Okay? So as I go up and down, the denominator changes, but as I go left and right, I will increment the numerator. Right? So then wouldn't this horizontal part that I'm making, wouldn't it comprise all of the positive and negative integers? Because it's all over 1. How could it be that if this right here, dot, dot, dot means it goes on forever. If right here is all of the integers, how could it be that the collection of all the fractions is the same number as this? Because I'm about to have, this is just one row. It's an infinite row. I'm about to have an infinite number of rows, infinitely long, to have a list of every fraction. So this would be 1 over -1 and 2 over -1. And let me line them up better. All I'm doing is having a system by which I can be sure that I have listed every possible fraction. Down here I'd have 1 over 2 and 2 over 2. See, this is 2 over 2. That's the same as 1. There's one's right there also. So some of them get repeated, but I'm sure that I have every possible different configuration. Here's 2, but this is also 2. Right? But I'm going to have, would you agree that I'm going to have every different type of fraction that could ever exist in this grid? And so I would keep making my lists go this way, and they would all continue. You can count these. This is a countable collection. It seems strange. It seems like there should be more of these than there are integers. But you can, but it's just because of the way infinity is working, you can count all of these. You can start right here in the middle and say, this is number 1, and that this is number 2, and this is number 3, and this is number 4, number 5, number 6, number 7, 8, 9, 10, 11, 12, 13, 14, 15, and you just do this forever. You will assign each one of them an integer satisfying countability. Right? It's like this pinwheel strategy for counting these things. So quite often, the point is that quite often, even if I have an infinite collection, it may seem that it would be uncountable, but turns out it actually is. Even if the, so it's going to be hard to have examples of infinite collections that aren't purely mathematical, because in nature, in the real world, you have never seen an infinite collection. Ever. No one has. Everything that you've ever seen is a finite collection. The Earth is made of a finite number of atoms. So the only way we could start to have countably infinite collections in nature is if the universe turned out to be infinite in size. It may be. It's something that at this point in time we can never actually know. So you can still have discrete collections that are infinite. And in nature, you'll have a hard time even finding anything to connect with that infinite. So you might be thinking, well, why would they bother at all to even talk about something that's uncountable? Here we did an infinite collection. It was the set of all fractions. It was countable. What about all the numbers between 0 and 1?
Count those two.
Can you?
Like 0.01, 0.02, 0.3, or 0.12.
More or less, yeah.
They can count those.
So so you're thinking like 0.1, 0, 0, so on, a bunch of zeros afterwards. That's what it would mean to be 0.1. It's that the rest of them were zeros. And then your strategy would be like to have 0.2 and then 0, 0.
0.3, 0.4, all the way up to 0.9, and it's a 1 then.
Let's say we did this. Let's say we did this. You would eventually get down here to 0.9000. And then how do I get to the next one?
10?
You want to do 10?
Is that it?
How do I know that this list will contain all of the different numbers between 0 and 1?
Question.
It certainly is. What's the difference between this number I'm writing right now and the first one on the list?
No, nothing.
Nothing.
The same number.
They're the same number. Let us do this. Assume for a moment that you could have some that would let you write down all of those decimal numbers, just in random order. Right? They don't order, right? We're just going to pretend, assume for a moment that there is some strategy that you could use to generate the collection of all of the decimal numbers. So that's like the first one on my list. Let me change this a little bit here. I'm going to make this infinitely long list. We're saying that we can count them. So this would be like the first one, and this would be the second one. And they all start as 0 point something or another. And maybe this one is 1, 6, 1, 2. And they're just in some kind of random order. Riley, you pick some numbers here.
3, 7, 9, 2, 8, 1, 5.
So that's the third one on our list. And this just keeps going. This one's going to be all threes. I mean, it's got to be on there somewhere, right? Regina, do you agree with that? I can, that if such a list existed, that it would be okay if it was all jumbled up, that not in any particular order. I could still count them, 1, 2, 3. Sound good?
I don't know, because I'm thinking if we're going from 0 to 1, who's to say, because if you're doing 0, the next one will be 0.00000. Who's to say where the end will start with 1?
It's a very good realization.
That's exactly what I was thinking too. I was thinking the same thing.
The thing is that in the real number system, 0 does not have an immediate successor, is what you're observing. There is, of all the numbers between 0 and 1, it doesn't have a least element. Okay? That's why you can't go through and make this nice ordered list, right? Because you'll always just be able to pick another one that's less. But what I want to do is just kind of gloss over that, right? Because I'm not really needing that fact. I'm not really needing to observe that fact in order to say that that number, whatever number you want, is somewhere on this list. Maybe that one that you were just talking about is right here, 0.000000. I'll just put a 1 right there. That was one of the ones you were talking about, right? And if we kept bringing it up a million more times after this, then we'd be at 1,000,005. There would be like 1,010 zeros and then a 1. Right? So every conceivable number you could think of would be somewhere on this list. My claim is that, my claim is that all of those numbers are on this list, and look, they have been counted. Now, what I intend to show you is that that claim is false. You actually cannot count all the numbers between 0 and 1. It is an uncountable collection. And how can I do this? I can very easily generate a number that could not possibly be on this list. Well, it's got to be a number between 0 and 1, so it's going to start off 0 point. And since this was the first one on the list that was claimed to contain all of them, then this number here is a 0. And so I'll just make this number right here 1 more than that. Okay? So then, without a doubt, this number that I'm building up here cannot be equal to this one. It's different from this number. Okay? Now, keep in mind, this list was supposed to contain all of them. We're going to produce a number not on the list. That means it can't contain all of them. Okay. Well, then, it disagrees. So this number that I'm building up here disagrees with this first one. How can I make it disagree with the second one? I will just go over here to this position where there's a 6 and make this one be 1 more than that. Make it be 7. So now this number that I'm building, it cannot be equal to the first number. It cannot be equal to the second. It disagrees with the first number in the first position. It disagrees with the second number in the second position. And then you just continue on in this way forever. This was the third one on the list, so I will make my number disagree in the third position. This is a 9, so I'll just make it cycle back around to 0. So in the third position, my number has a 0. That way, it disagrees on the diagonal of this list. Right? Sorry. So I made that a 1, this is 6, I added 1, that's 7, the 9 becomes a 0, that's a 3, 4, and then this down, I'll make this a 1, and by this construction, you have caused a number to be created that could not possibly be on this list. So if someone were to claim, I have made a list of all of the numbers between 0 and 1, they're mistaken, because if they made such a claim of all those numbers, then you could count them. And just like I can count each of these integer positions, I can construct a number that disagrees, that is not equal to each and every one of the numbers on this list. Wouldn't you agree that this list is infinitely long? It exhausts all of the integers, right? Because this was the first one, this was the second one, third one, fourth one, fifth one. Clearly, I'm going to go all the way to infinity, right? It's going to be an infinitely long list. So this is an infinitely long list. All of the integers are used up, and then this guy up here is not on the list and does not have an integer assigned to it. And there are no more integers to assign. We ran out. So the collection of all the numbers between 0 and 1 is uncountable. This interval from 0 to 1 is uncountable. Now,
Hold on, I have a question.
Yeah.
So if you say that list of all the numbers from 0 to 1, so 0 point numbers to infinity, that list goes to infinity, wouldn't somewhere in that infinite list be that number that we can't technically count?
no.
Like with the whole...
Let's recap why it could not possibly be in that list. Because by the manner in which we constructed this number,
Just by going one above the next number.
it must disagree with each number in this listing.
What do you mean it must disagree with it? What do you mean by
Because
disagrees?
here in the fourth position, it disagrees with the number that is listed as number 4. And here in the second position, it disagrees with
So
the
you're
number.
saying on the infinite list, on the infinite diagonal line, each number on top will be different from all the numbers that it's on the
Yeah.
diagonal line. Okay.
Yeah.
Okay.
You can construct a number that could not possibly be on the list because it would at least disagree somewhere.
Okay.
Now, there's going to be some number that starts off on this list. There would be a number that starts off 17041, blah, 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 blah. It might agree for 1,000,000 digits. But then there will be some digit where it's different.
Okay.
And so then that means that you can't count all of the numbers between 0 and 1. It must be uncountable. Well, what kinds of abstract things in your real day-to-day existence are like little chunks of the number line? Because that's what this is. It's a little chunk of the number line. It's a second of the number line. What kinds of things would you encounter? I mean, I'm not going to encounter this here collection of things that's uncountable, but there are uncountable things that we use and encounter all the time. You used it today. I've already talked about one of them today. Besides this thing.
What about the numbers between 1 and 2?
Okay, yeah. You could extend that to say that any interval of the real number line is uncountable. Well, what kinds of things in your real life correspond exactly to intervals of the number line? So you're going to be a nurse. You take your patient. You're just working at a regular doctor's office. What's the first thing you go and do
Check in.
after that? You get your patient, and then
They get their vitals.
okay,
It says them.
nothing going on. Anything going on there?
No. Well, just, yeah, numbers with the vitals and stuff.
Numbers with the vitals. What kind of numbers you taking?
Well, blood pressure.
Let's talk about heart rate.
Respiration.
Let's talk about heart rate. So it's you can in heart rate is discrete. Talk to me about their blood pressure.
Well, blood pressure.
Let's pretend you're doing it manually.
Yeah, you gotta, like,
Doing it
how to
manually.
do
When
it.
you look at looking at the little gauge, does that needle jump to different or smoothly transition between them?
So it will,
When you're driving in your car, does it say 20 and then 21 and then click 22 all the way up to 70? Or does it smoothly transition between all of them? When I talked about the variable of height, right? Each of us has a height, but heights would be measured like with a tape measure. And the tape measure, even though it's graduated with into eighths of an inch, if you only change the precision with which you are reading that tape measure, you can obtain any level of precision you want. Heights are on a continuum in this way. They are continuous. There is an uncountable number of possible heights. There's an uncountable number of possible speeds to drive your car. There's an uncountable number of different blood pressures. If we don't simply relegate ourselves to the whole numbers, your blood pressure is 115 over 70. Well, why couldn't it have been 115.0006038? As long as you want, just as precise as you want. Nobody's going to do that. It doesn't help a lot. But that doesn't change the fact that it is on an interval. Virtually anything that you're going to measure is continuous. Virtually. Right? Things like distances. Continuous, right? Because they have a correspondence exactly to the real number line. Any point on the real number line can be mapped directly to some point on a ruler, right? So if I had, or think about a temperature scale. Here's my horrible drawing of a thermometer. And it has these graduation marks. And it's an old-timey thermometer, so the mercury has to rise up, or it's not even mercury, it's something else. And you're looking right there. But really, if this is a thermometer, how is this materially different from another? Where this section right here is a segment of that number line, and the actual temperature is one of those crazy points in that segment for which there is an uncountable number of them. I mean, this might as well be labeled 0, 1, 2, 3. Point something. Eventually, for you to get your job done, you will have to just
Figure out what closest to you.
choose like where to stop. But you would understand that the number you wrote down is different from the actual state of the actual temperature. It could be microscopic, inconsequential even. But it could have been any value in between here and here. Take a cup of coffee, hot coffee, set it on the table, stick a thermometer in it. The thermometer comes up to whatever temperature the coffee is, right? But let's just let it cool. Let the coffee just cool down until it's room temperature. And then the mercury in that thermometer would have traced out every possible temperature from its maximum all the way down to room temperature. So things like temperature are continuous. They're uncountable. There's an uncountable number of possible temperatures. There's an uncountable number of possible lengths or areas or volumes. Anything to do with measurement is going to more than likely be continuous. Things that I'm going to go and actually put my hands on. I can go actually, I can't put my hands on your heartbeats, but I can certainly count them. Okay? Because they by their very nature, they are accountable, right? You have the first one and the second one, and then 4 billion later, that's the end of it. But yeah, just by their nature, they are countable. And most of your measurements, like even time, that one's actually up for debate. In the future, we will probably learn that time is quantized, meaning it comes in little discrete chunks. In the last 100 years, quantum physics has become incredibly popular, incredibly useful, and has led to a lot of scientific discoveries. And that word quanta just essentially means you have discrete chunks, you have little pieces, right? You can count them. You can count them. And so we've always thought of time as being continuous. And we've always thought of like length as being continuous. And for the purposes of doing this course, we will continue that. In the future, though, that may not be the case. It could in all likelihood turn out that the only things that are continuous could be things like the real number line, abstract things. And that probably everything in the universe is quantized on some level. But here in this course, the questions that they've asked you are also somewhat misleading. So they'll ask you something, and what you'll just be looking for is, are they talking about measurements? If so, it's going to be continuous. Are they talking about the height of buildings in Chicago, right? If they're talking about the height of buildings in Chicago, well, you would not say it's countable, even though that's probably the correct answer, because that's not what they really meant. If I went to Chicago, I could visit every single building. I could measure every height of every building and count up all the different heights of all the buildings in Chicago. But what they really meant was, what are all the different possible heights for any building that I could ever build in Chicago? So you have to read a little more into it. So on some of these questions that they'll ask us, we will have to do some of that reading between the lines. There should be 2 or 3 questions on this in the homework. Let's go ahead and do them, and then we'll take a break.
Kind of a mind-boggling thing to think about, though.
It is.
Measurements aren't exactly the measurement you think it is.
That's right.
Magic chemistry, no, she can't say
I honestly don't remember anything she taught us.
it was about measurement.
I actually, you know what's funny? I asked her what like significant digits were, like
Yeah.
why they're significant, like what's the, I said importance, and she corrected me and said significant like 4 times. I just want to know why they're so important.
Look, they are crucial. Look, because
Terrible.
if I ask you, let's say we're in a compounding pharmacy, right? And we're needing to make a medication, and they say we need 1.2000 milligrams of whatever medication. Okay? And you go over to your little digital scale. Here's your little digital scale. And you go to weigh out that medication. And right there on the screen, it's saying 1.2015. Okay? If the prescription says this, then you're off. You're off by that much. Okay? I have significant digits here all the way out to the 4th decimal place. The prescription said, don't put 1.2 milligrams. That's not precise enough. I want the next digit to be a 0, and the next one to be a 0, and the next one to be a 0. And you're not allowed to deviate from this until the digits after that. The digits after that are insignificant. These are significant.
That's all I needed to know.
Right.
Easy explanation.
If the doctor said 1.2 milligrams, then that is 1.2 milligrams. 1.2. Who cares about the rest of it? They're not significant.
You ever thought about teaching chemistry?
I have.
Probably good.
Okay. And that's significant. The numbers of channels on different televisions. The numbers of, so you get you have yours open, and we'll work mine, and then if you can't figure out yours, or if yours is materially different, we'll do yours. The numbers of channels on different televisions. Tell me what you think. Yeah, yours will be a different question, but the let's answer my question, and then that should and then hopefully
But
that will
our
help
answers are
us.
the same as yours, though.
Yeah. So can I count up? Let's say I just look at the first television. Could I count up all the channels? Yes. And then let's move on to the next television and keep counting, right?
Yes.
And then the next one and keep counting
Yes.
until I've counted, until I've gone to all the televisions.
Yes.
Will I ever run out of numbers?
No, it's the first.
It's countable.
Yeah,
It's countable, so it must be discrete.
To the eighth.
It must be discrete, and the number of channels would only take on specific integers, right? There's 100 channels, or there's 10 channels, or whatever. The variable in this case would be, this is the variable, right? So I would go to the first, I would go to, this television here has probably just one channel, this one, right? And if I went to my house, there's, however many channels. And if I went to the hotel, there'd be, 15 channels. And so each time it's just a different integer that goes in that spot, because we can always count up how many channels there were. All right, what do you guys got?
Well, I had the heights in inches of female students at a college. I already answered it, got it right. The data are continuous because the data take on any value.
Right. That's one of those questions that are worded incorrectly, right? If I went to a college any college, and measured, I mean, there's going to be a finite number of women there, right? So then correspondingly, I'd have a finite collection of heights. I could count them. It's not really what they meant. They really meant to say all the different possible heights of any possible woman at any possible college that could ever exist. Well, then now we need continuous, because if I'm going to talk about any possible height, there's a whole bunch of them. There's an uncountable number of them, because it's a measurement. So as soon as you saw height in inches, it was like, it's over with. It doesn't matter what anything else that they said was.
If I can count it, it's just, I already know that's gonna be.
Yeah. All right. How'd you do?
It says the square footage of houses that have a colonial style in different cities. It says that square footage of the distance. So I put the distance or continuous because the data can take on any value.
Yeah. An area is a two-dimensional version of a length. Right? Length times width. And a volume is a three-dimensional version of a length. Length times width times height. So lengths, areas, and volumes are all going to be continuous. Question 2, the exact mass in grams of food eaten by a person each day.
If it's exact, then it should be, that you can count those. Not the grams, but calories.
Can I count all of the different possible
Oh.
values of a weight that could ever be? And that's what this is about, technicalities. Technically, we cannot. I can say 1 gram, 2 grams, 3 grams, but that has a direct correlation between the numbers 1, 2, and 3, for which there's an uncountable collection between 0 and 1, and 1 and 2, and 1 and 3. So, conceivably, you could construct some food that can be eaten by a person of each different possible weight that could ever be. I could have someone eat 100 grams of food, or I could have them eat 100.0000001 grams of food. And I just keep sticking a 0 in here, pushing that 1 down further and further. It gets closer and closer to 100 grams, but never quite is. And even that collection is well, as soon as we start talking about something that can be measured, in all likelihood, unless it's I wish I could figure out how to say that, because the heartbeats thing is, your pulse is clearly discrete. It's like when you're driving in your car, you know, the speed limit is 55 miles per hour or whatever. But you don't get to in an instant jump from 50 miles an hour to 55. You had to go through all of the different possible speeds until you stopped accelerating at 55. And so much in the same way that you have to trace through all those possible speeds, I can construct a dinner that traces through all of the different possible masses. It's always coming back to this mapping with the real number line. Right? Anything that can be mapped onto the real number line, 1 to 1, where each different mass maps over to a different point on the number line. It would be a very easy mapping where n number of grams maps to the number n on the number line. Right? So 1.20025 grams maps to the number 1.02250. And so all of the real numbers would be used. There would be a real number for every single different weight. Look, all you're really doing is just sticking a G on the end of all of the real numbers. So in essence, this collection of masses is exactly the collection of real numbers. continuous because it can take on any value in an interval.
So I actually have a question on one of these answers though.
Yeah.
It says like the continuous data only,
Yeah, those two are just flat out false.
yeah, the one with specific values, because I don't think you can do
Yeah, you
continuous
can't.
with specific values, right?
You cannot. So C could never be the answer no matter what, because the idea of continuous and specific are mismatched.
And then you can't do discrete with intervals because
Right.
you can't count intervals.
That's right. They just wanted 4 answer choices, so they just,
So you just flip flop words.
Yeah.
Just discrete out.
yeah. Do you all right?
Well, I have a question about one of these that I saw,
What is it?
and it says the number of fingers that different people have.
Okay.
So I could understand, like, it's talking about, like, people, but you can count them.
Right.
So I put the data are discrete because
Because they can take on
On
specific value.
yeah, but it's really wrong.
Let me read your question.
I put that one.
Is this really number 15?
No.
Oh, I see.
Just
Number
2.
2. The numbers of fingers that different people have. Do me a favor.
Should I do the bunch?
Click the final check, but then we're going to click something else. Don't get in a click area. Oh, it's okay. Are you sure you had the right one?
Yeah.
You didn't have discrete, and it takes on any value in an interval.
Because that didn't make sense to me.
Okay.
I don't know.
Okay, so we're happy to find that we indeed can count fingers. That's how I learned to count, I guess. And yeah, people are gonna, even if somebody was, born in the vat of radioactive liquid, and they had thousands of fingers, he could still count them. So, or if you didn't have any, it wouldn't take long to count them. At either rate, they are countable. Any other questions, Regina?
This one says the movie ratings of a critic with possible ratings being 0 stars, half a star, 1 star, and so up to 5 stars.
Are you sure you're not on question 3?
This is question 2 for me.
Question 2. Oh, okay, I see. So read it to me again. It's
The movie ratings of a critic with possible ratings being 0 stars, half star, 1 star, and so up on to 5 stars. So that's number 1. Number 2.
This is a listing of all the different possible ratings. Right? They could get a half star, they could get a 0 star.
So it'll be continuous then.
Oh, would it? That's a rating of 1. This is a rating of 1.5 stars. This is a 2-star rating. Can we give someone a rating that's not on this list? But they told us there's a restriction that the ratings are in half-star increments up to 5 stars, starting with 0 stars. That generates a finite collection.
So that gives you a counting thing, so you only do half stars to 5. I can only get half stars up to 5, so
Yeah.
you count half.
So basically, they have told us you can use. Well, here's what they've done. They've said, give people ratings from 0 to 5, 0, 1, 2, 3, 4, 5. You can give them any of these ratings, and you can also give them half ratings. It's kind of like shoe sizes, if you will, right? They got shoes that come in whole numbers. They got half sizes. They don't have shoes that are just any specific size that you want in the whole world, right? Eventually, there's some degree of precision, but they're not going to bother with it. So it's countable, and because it's countable, you can only have this many different
And
ratings.
that's what it means by, they can take on any value in an interval?
No.
Instead, it'd be specific because you only have.
These are the specific ones
Okay.
that it can take on. And I think number 3 is a different concept.
It's nominal,
Okay.
ordinal, interval, and ratio.
So when we come back, we will do that. Let's take 10 minutes.
Is there a bathroom on the third floor?
There is.
Okay, cool.
It's over on the other side of the elevators.
All right, thank you.
Do they have good snacks down
Yeah, they're kinda light. We got chips and other shit, but. Made a good decision being in person though, legit. He helps us out a lot. I had him for algebra or some shit. Literally, we did the fucking midterms in class and like 10 minutes. So now he's a fucking piece of G.
there? Yeah, I can do a math class. I can barely do classes online because mine, I just,
Nah, me too. Me too.
so I have to be in person, especially like a math class.
Oh fuck, no, I'm not trying to do math on a damn computer. You kidding me?
They basically be teaching me stuff.
No. What other classes are you in?
I have my first, was it Foundations of Higher Education tomorrow.
Oh, this is your first term at like sergeant? Damn.
Yeah, so this is my first class. This is my first day of class.
Oh, nice. Oh, yeah. How many pre-reqs you gotta do?
I think I had like 4 or 5. I know they didn't take my statistics. Well, I didn't take the statistics, and then they didn't take my, what was my other one? I don't know, I have to retake pharmacology. I have to do patho. And there's one other one that I have to take, I can't remember what it is.
You have to take like chemistry, physiology, anatomy or anything? Any English classes? Oh, yeah. You gotta do like, cause I'm in lifespan psychology and oral communication in this one.
You know what, I think I have to do lifespan. I think I don't understand that.
That one's all online.
I guess I'll cross that path when I get there.
Honestly, like, the online classes, you don't really learn anything. You just kind of do the assignments and turn them in.
Right.
That's what I, for psychology, I did all of my shit the night of it was due. It was super easy.
Oh.
So the online classes are pretty easy. It's just like trying to learn math online is dumb, so. But yeah, like I know all the science classes are in person.
I did my first nursing degree, online because that's the beginning of COVID, and that sucked. It sucked so bad. So I was like, never again will I do that. So all the in-persons I can take, I will take.
What did you do? You did RN online? They
I
had
did
that?
my LVN online.
Oh. Oh,
It
yeah.
was supposed to be in person, but since COVID happened, they changed it to online, so.
Are you working as an LVN right now? How do you like it?
It's okay. I work at a plasma company, so I don't do a lot of, I do more so physical, so like assessments, but all the rest of the nursing things, it's easier,
Yeah, good money too.
yeah.
Oh, yeah.
Once I finish this and get my BSN, I think I'll go to like a hospital or something.
Honestly, I'd be a fucking, I kinda wanna go work at like a plastic surgeon office.
I don't know,
Just fucking assist with, you know, girls getting fake business. Just get paid hella
Just
money
pay,
to
yeah.
do that, you know? Like, I'll just be the surgical dude next to him and be like, double.
You wanna work in
It's like,
surgery?
good job, good job.
That was my field.
No, plastic surgery.
Oh, plastic surgery.
Cause that shit seems chill as fuck.
Surgery for assholes.
Huh?
Surgery for assholes.
Honestly, they can be an asshole when he wants to me if he's paying me good. Fuck.
Shit.
I'll sit there and shut the fuck up.
I got
and
into
say
it with
nothing.
one and he broke scrub, told me get out, we'll never work in a room with me, happened twice.
Oh, wow.
But I got one guy, Dr. Patino, who's like Colombian, you have a mask, you know, and he already can't understand what he's saying. So he's like, and I'm like, trying to get clarification, you said you wanted this, and are you fucking stupid? Blah, 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 blah. And I'm like, I can't read your fucking lips, and you can't speak clear English, so I'm just making sure I'm giving you
Wait, what was his ethnicity?
Colombian,
Um,
you know, and then you're stupid, blah, 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 blah. All you had to do is say yes or no, because I cannot understand you with all this stuff going on. And, you know, and then you're down there and I'm back here, you know, I just need clarifications, but they're assholes. Like, the
no,
orthopedic-
doctors are fucking cunts, dude. I'm not gonna lie. Like when I was an EMT, and like the doctors would just talk down to you.
I'm like, what the fuck are you
And
talking
then it's
about?
all like,
Yeah.
and they're all like, you know, so, you know, you basically just like give your report, like you tell the doctor what happened. I had this one doctor's like, well, clearly you don't know what you're talking about. And I'm like, bitch, motherfucker, shut your punk ass mouth,
Yeah, I got
dude.
a mouth, so
I'm
yeah.
like,
I'm
I
like-
kept them alive so they got me.
No, legit, I was all like, he goes, well, I guess someone doesn't know what they're talking about. And I was like, well, you know, to be fair, I was like, I showed up there and nobody told me anything. So I'm only going off of what the paperwork is telling me. And he goes, yeah, okay. And I was like, honestly, fuck this dude. And I obviously can't say anything to him, he's a fucking doctor. And like, and I'm a fucking EMT, I don't know shit. But understand my fucking situation, dude.
Right.
I don't know anything about this patient. By the way, they're fucking mute. They can't talk to me either. So I'm just going off literally what the paperwork is fucking telling me. And then he just like does his little bullshit ass assessment and then fucking walks away. And I'm like, dude, fuck this motherfucker.
And not only that, they had years of education behind that.
And they don't teach you, they just expect you to know it and anticipate their needs and jump when they say jump.
Now I will say, I have met doctors that are very humble about shit, and they're like good doctors and stuff like that. And I would tell them like, hey, I don't really have much to go off of. This is the situation. He goes, all right, cool, yeah, we'll take some tests, we'll do whatever. Good job, thank you very much. And then you get the doctors that are just like assholes. And it's actually funny because I was waiting on bed delay to get a bed and shit, and this girl comes in, she had an allergic reaction, and her mom was with her. The mom's a fucking nurse practitioner, and so she knows everything that needs to be done, and the doctor comes up and tries to outsmart her. He didn't know she was a nurse practitioner. And then he starts like saying a bunch of stuff, and she's like, I'm a nurse practitioner. She needs this, and that. Shit on this dude entirely. He was like, oh, okay. And then he's like, oh yeah, by the way, this is this and that, and like blah blah. Don't give her this medication, don't give her that because it's gonna do this. And those are the medications that he wanted to give her. With that, like, it was funny as hell. And it was amazing because that doctor's a fucking asshole too. Like he legit would just make sure there's a crowd, and then he would just kind of like openly shit on somebody to make himself look better.
Right.
And I'm like, dude, I hope you get. I'm like, you know what? I was like,
I
I hope you get in a car accident with your fucking Tesla, and you have a nice electric fire. That dude was so mean for no reason.
I can see like the PA, they just didn't try their surgery, they were going fine. I'm like, why you letting them be probably I was on this? So they can kick me out of the circular hospital. They might end up doing something.
It's so beautiful.
Look, you don't have to be disrespectful. You don't. Don't cuss me out now.
There are 4 levels of measurement. So we declare some variable. We're going to go and collect the data associated with that variable. And that variable could either be discrete or continuous. And it can also be one of these 4 categories. Any of them can fit into any of these. Well, I take that back. This one can be discrete or continuous. This one can be discrete or continuous. And these 2 can only be continuous.
Ratio and interval can only be continuous.
That detail won't matter to us. It's just true. And I have them listed in this order, not because one of them is like better or more preferred than the other one, but nominal is like the lowest order. Order is the wrong word. It's the most rudimentary. Rudimentary. And they increase in complexity from here to here. So it's like everything that you would measure is at least nominal. But can it graduate up to be ordinal? Okay, if it can it graduate up to interval or ratio? And so the word nominal implies that there's something going on with just a name. Things at the nominal level of measurement are simply replacements for names. For example, your driver's license number. Your driver's license number is a number. It's just a replacement for your name. No one else has that number, right? It's a stand-in for your name. It's composed of these 8 digits, and theoretically, you could sort those driver's license numbers into an ordering. But would it be the case that the person with the lowest driver's license number was the first driver? No. Are they the best driver? No. In fact, trying to establish that ordering on this just does not mean anything. It's not meaningful. It's not a well-known ordering. I mean, a numerical ordering is well-known, but to numerically order the driver's license numbers is not illuminating anything at all about the people associated with those driver's license numbers. So putting those driver's license numbers in order won't tell us anything about the data set, right?
It's the same with like the social too.
Yeah. When they first introduced the Social Security numbers, like the people that were around that didn't have one, like I remember my father was in grade school when they introduced them. And they brought the stack of cards in the room and just handed them out. And they were all sequential. So like people that he was in class with had Social Security numbers 1 number away from him. It was just like the next card on the stack. It didn't mean anything. It doesn't. There's some kind of sensation there where the Social Security number could mean something like you were among the first people to get them, But I do not believe that they started off with 0000001, right? Each of those segments means something. Take your phone number, for example. You could sort them in numerical order, but that doesn't tell you anything, right? Zip codes, you could put them in numerical order, and they will somewhat tell you about an east to west configuration, right? So the ones on the east are very low, and the ones on the west are very high, but they won't be perfect, and it won't tell you anything about north and south, and it won't tell you anything about this city's better than that one or anything like that, or this city was first and that city was last. It's just not meaningful. It's not a well-known ordering. A popular example from the homework will be jersey numbers, right? Jersey numbers must be a replacement for a name because if you had two people on the field with the same jersey number, there'd be a problem. And if you sorted all those numbers from like least to greatest, it's not going to tell you who's the first one on the team or who's the best one on the team. They don't mean anything. They're just a replacement for your name. Ordinal is for when we have something that's at least nominal, but also has a well-known ordering, right? So my typical example of this is gold, silver, and bronze. If you came in first in the Olympic event and then they took you to the podium and gave you a bronze medal, you'd be upset because everyone knows they go gold, silver, bronze. 1, 2, 3. They go in this order and no other order, and that's the well-known ordering. You do not have to have things that are numerical in order for them to be at the ordinal level of measurement.
So it's a replacement for a name, but in an order.
Right. Tell me another example of something that you know, and you have known for a long time, that is not a number, it's not a collection of numbers, but it is, have a well-known order.
Great.
A, B, C, D, and F. What's another one? What's the most fundamental non-numerical ordering? Alphabetical order. If somebody started rattling off all the letters of the alphabet in some crazy ordering, we'd know it, you know?
D, F, G, Z, Y, Q,
Yeah.
A.
Like, that's not how it goes. It's a well-established ordering that everyone agrees on. That's ordinal. You can also have things that are these last two are very similar. They just have only one distinction. So how are they similar? They are similar, and we use this phrase. Differences are meaningful. Now, this phrase doesn't exactly restrict you to always looking at subtraction. What it means is that what it truly means is that it's closed. So, for example, if I had I'll give you an example of something that's not closed. Movie ratings. Movie ratings can only be ordinal. If I have this movie here and it's got a 2-star rating, and I've got this movie here and it's got a 4-star rating, I can't merge them into one movie that has a 6-star rating, right? It doesn't mean anything. If I took the 4-star movie and whatever it would mean to subtract away the 2-star movie, I would not have another 2-star movie, okay? It's not close. The difference of 2 movies is not another movie with a rating. However, if I had a cup of coffee that was 80 degrees and another one that was 100 degrees, then the difference between those two is a temperature. That means something. It's 20 degrees difference. In fact, interval level of measurement, it must be the case that differences are meaningful, but 0 is not a start point. Whereas with ratio, 0 is the start point. And even start point is not really the best word. Maybe it should say the least possibility. Because for temperatures, there is no least temperature that can be obtained. You may have heard of the Kelvin, if you've just finished your chemistry class. You have the Kelvin temperature scale, which has this concept of absolute 0. But that's an idea from physics where if it could be the case that any system could obtain the temperature of minus 273.15 degrees Celsius, then it would have no more energy. All of the molecules would cease to move. But that's impossible. Electrons will have a fundamental, they have a spin, so they'll always be moving. So it cannot be the case that you can cool anything all the way to absolute 0. You can only get closer and closer and closer. It's an asymptotic limit, but we can keep getting colder and colder forever. We can get closer and closer to that. We never will. We just keep getting closer. Just like we can keep getting hotter and hotter, and it could be so hot, and I can say, let me add 1,000,000 degrees, and it won't really make a difference if it's already 5 trillion degrees, in temperature. So if we're looking at the temperature of a supernova, and then I say make it 1,000,000 degrees hotter, no one's going to notice. It's microscopic at that point. So and it's in the same way. I'm approaching infinitely hot or as cold as it could possibly be. It turns out there's actually not just like there's an absolute 0, there's an absolute maximum temperature. It's called the Planck temperature.
Is it Planck or point?
Planck. There was a physicist named Max Planck that redescribed all of the units of measure in a more natural ways that were based on things like the speed of light, and just a minimal set of measurements. I think there's just 4 of them, and they're much more useful for investigating really complex ideas from physics. In fact, that's one of his system of measurements is one of the reasons why his systems of measurements gets used for how I was saying earlier that everything seems to be quantized. Even space itself, it doesn't seem like you can have as small of a length of distance as possible. The smallest such length of distance that is meaningful is the Planck length, because anything that would be smaller than the Planck length, if you tried to look at it, you would need a frequency of light that was so high energy that as soon as the light hit it, it would just form a black hole. You can see it anyways.
Where they got that movie off of, that new Marvel movie, Quantum something, is that the same kind of thing where they were lost into
Well, that dumb Ant-Man movie?
Is that what it was? I didn't see it, but it's kind of like how you saying, like it's just.
It's become more popular it's more mainstream these days, like to have these type of ideas and enter into the
Kind
mainstream.
of like how you said it went to an area of space that they couldn't come out of and had to figure out how to travel something.
Yeah, basically Ant-Man's, or the doctor's wife was like stuck in the quantum realm. And like, are you talking about that
So
kind
that's
of
like
thing?
a black hole.
Not really.
Yeah, well, I mean, a black hole is something that's so gravitationally it's so compact.
Or are you talking about Interstellar, then he found out time is the fifth dimension or something?
I can't remember. It just kind of just reminded me of what he was saying.
You can compactify a mass such that the gravity is so intense, light cannot escape it. And how do we see things? The light has to reflect off of it. Well, if the gravity is so strong that a photon speeding away gets pulled back, then you can't see it anymore. And so likewise, there's this abstract limitation where, so light is energy. The Einstein said E equals mc squared, but that's not the whole story. It's actually E squared equals m squared c to the fourth plus v squared c squared. So if you take square roots all the way across, you can see here where you would have an E equals mc squared. Just reduce all these by a half and ignore that part. This part over here is having to do with light, and this one is having to do with things that have mass. So light does not have mass, but it is, at its essence, just energy. And as you increase the frequency of that light, then the more energy it carries. So visible light has a certain frequency, and above that, you have ultraviolet light, right? That's even higher energy, like that's what gives us sunburns. Beyond that, you have microwave light. Beyond that, you can have gamma rays, and they're extremely high energy. If you got hit with gamma rays, it would kill you eventually from radiation poisoning. And if you just take it to its natural limit, as high a frequency as you could imagine, as high a frequency as you would need to view this ultra microscopic length, it's like a trillionth of the diameter of a hydrogen nucleus. It's very small. Try to look at something that's that size. Well, if the light, I would need one entire wavelength to fit inside there. And if we were to create light that powerful and try to look at something that was that size, you still couldn't see it, because that amount of energy in that space would just become a black hole, because it's such a high amount of energy in one little spot. So what was the point of all this?
You just got down a gnarly rabbit hole, dude.
Virtually everything is going to be discrete or quantized. There is no minimum. There is a minimum such temperature, but we can never reach it. So even if I said absolute zero as my starting point, it won't work, because just like how if I was looking at the number zero, there's not a next number immediately after zero. So there's not a least such temperature that you could ever actually have, right? You could always keep getting colder and colder and closer to absolute zero. There's also not a maximum temperature. That was the Planck temperature. However, for ratio measurements, zero is the start point, right? And my usual example up here is the amount of time you might be waiting in like a line at the grocery store, for example. As soon as you enter the line, the moment you enter it, you've waited 0 seconds, right? And it just goes up from there. What's the least amount of time you can wait in a line? 0 seconds. I didn't wait in that line at all. I waited 0 seconds. It couldn't have been negative seconds, unlike interval, right, where you can have it be minus 10 degrees, right, on like Celsius, for example. So otherwise they're the same. It's just that this one starts at 0 and this one doesn't. The canonical example for interval is temperature. There's really not a lot of other examples of stuff at the interval level of measurement besides temperature. I seem to never be able to remember one. But we can certainly think of some at the ratio level of measurement. Can you think of one?
You're born, you're 0.
Yes. Your age. Your age is at the ratio level of measurement. That's a perfectly good example. All right, let's look at the problems. Oh, my session ended. Which of the 4 levels of measurement is appropriate for favorite types of music? So we've got all these different types of music. Nominal.
Because you have one, most favorite, second, third, fourth, fifth, sixth.
You're thinking of order.
That would be,
Yeah, isn't that the order?
No.
Oh wait,
Ordinal
ordinal
is
is the order.
Nominal's name.
Nominal is names.
Favorite type, you know, the genre.
Why should your list of favorites be the same as anyone else's,
Okay.
right? So you can order your favorite types of music. We might say the songs that play on top 40 radio are pretty much everyone's favorite types of music, but not really, right? So there is no well-known ordering for favorite types. And that's the key. There are orderings, but they're not widely agreed upon, without question. So here we are just left with nominal. All right, what's y'all's?
Number 4.
I got on the first one. Mine was favorite sports, and I put nominal. It was a lucky guess.
Why?
And I'm on number 4.
Why is that lucky guess? Wait,
Oh
back
no,
up.
because I answered that question before we got the
Oh, okay.
explanation of what they were.
I got you.
But now my question 4 says acres of land,
Acres of land.
which acres is another form of a measurement.
What's the smallest amount of acres of land that you could ever own?
I would say ratio.
0?
0. That's why it's ratio.
Let's see.
Because, I mean, we can't say that, you know, how much acres of land do I own? Well, -2. That doesn't make sense. 0 is the starting point. It's the least quantity of acres of land you could ever own.
I have one. It's yes or no. Wait. Survey response of yes, no, and no opinion. So that wouldn't be or no.
It would not be ordinal. Why not?
Because there's no order to it. It's either yes, no, or no opinion.
Right. I don't know how to put those in order.
And then it wouldn't be.
Then it would have been nominal.
If it doesn't go above ordinal, it doesn't go anywhere. It stays at nominal. Everything is at least nominal. Can it get higher? That's the question.
Oh, so it's nominal.
Nominal. As soon as it doesn't graduate to ordinal, it's stuck forever at nominal.
So if it's nominal and ordinal, then it's obviously going to be interval ratio.
No.
That makes sense.
If it's nominal and ordinal, then it's at least ordinal.
Okay. But if it's not ordinal.
But I don't know what it's at most. Right? It would only still be ordinal if it was at least ordinal and at most ordinal. Can it become interval or ratio? That's where you'll have to look at can I take the differences of two things? So like the movie ratings is going to be a good example, right? If you see one that's about movie ratings, okay, think about, let's see if I get one that's movie ratings. Oh, here's my yes, no, no opinion, so that's nominal.
The voltage measurements of batteries.
Okay, hold up on that one. This is like the voltage measurements of batteries. Okay.
I'm gonna say.
Kiara, what is the minimum amount of rainfall I can have in a given month? 0.
Really?
So we know.
It'd be ratio.
Ratio. Ratio.
Because ratio can be 0, but interval can't be 0.
Right. If we could somehow have a negative amount of rainfall in a month, this would be interval. If I could somehow check the voltage on a battery, and it would be negative volts. Now, that is possible. Just interchange the poles. But what they're meaning for you is to not do that. Always check it, positive to positive, negative to negative. And you can certainly, differences are meaningful if it was voltages, because if I had one battery that was 3 volts and one battery that was 4 volts, and I took them and put them in series and checked the overall voltage, it would be 7 volts. Right? Voltages are additive in that way. So differences are meaningful, and 0 is a starting point. A dead battery is 0 volts. That's as low as it could go. All right, did we all do through number 5? Kiara? Mm-hmm. Okay. Then, after that, there's 5 different ways to collect a sample. Five different sampling techniques. And I want you to approach these type of questions like there's a flow chart. Okay? You're gonna say, okay, there's the example, there's the what they're talking about. And the first thing that we'll check is we'll say, is this sampling technique, is it systematic? This is not the word systemic. My nursing students see the word systemic probably a lot more than systematic. So it has this root word of system. And it helps us to remember that there's going to be a well-defined, rigorous way to pick like the next one. Right? I'll have a system to pick the next one. What you'll do is you'll start at any, you'll have a numbered list of all of your population, let's say. Pick any place to start on that list at random. Maybe you start at number 45. Okay? And then, if I'm starting at this random place, 45, how do I get to the next one? Well, here's where I'll have another random number. I'll have another random number. Maybe that random number is 11. Then my first one would have been number 45. My second one would be 45 plus 11. And then the third one would be 45 plus 11 plus 11. And the fourth one would be where I add 3 of these 11s. So really what I can say is that it should be times some number n, where n just varies between 0. Let me not use n. N's going to be busy. We'll say k, where this k varies between 0 and n minus 1. Why is it? Well, why have all these symbols? Well, it's because the size of the population, what do those vertical bars mean? Think back to algebra. Absolute value.
Absolute.
Yeah, you're counting how many is in the collection. So the size of the population is capital N, and the size of your sample is lowercase n. And this is agreed upon worldwide. If I'm ever using a lowercase n, it's the size of the sample. The size of the whole population is capital N. Now, how many different choices do I have here for this k? It could be 0, or it could be 1, or 2, and so on, all the way up until 1 less than my sample size. But how many numbers are there right here? It doesn't start at 1, it starts at 0. So there are n many choices here, right? Because that was the first one, and this was the second one. And then all the way down, this was the nth one. Do you see it? Because each time I just add 1. I just take that and add 1, and that's the number it gets assigned to. Right? So there are n many different. This will build for you a collection of length n. Let's say I wanted a sample that was just size 4. So k would be 0, 1, 2, or 3. Okay, because if my sample size is supposed to be 4, then I will stop at just 3. Then I have the 4 different numbers. So then number 45 will be my first one, because it will be 45 plus 11 times 0. And then the next one will be 45 plus 11 times 1. And then 45 plus 11 times 2. And 45 plus 11 times 3. And that would be all 4. That would be the way I pick the 4 members of my sample. This is a systematic technique. This is something you would see like at a factory, right? You've got an assembly line. You've got just a whole bunch of these things you've got to look at. You can't go inspect maybe you're quality control. You can't go look at all of them. So you have some sort of system here. We started in a random place. We have a random step size, and I'll start here, at the 45th one, and then pick every 11th one that comes off the assembly line, and that's how I did my sample. Okay? That's a systematic sample. It will be very easy for you to detect if you are dealing with a systematic sample. That's why I want to check for it first. Right? Because inevitably it would say something like you're choosing every 25th person off the list. And it's like, boom, it's systematic. If it's not systematic, then you have to ask, is there a partition? Is there a partition? A partition is kind of intuitive, but it can have a rigorous definition. I'll give you an example. When you were in high school, you were partitioned by being freshman, sophomore, junior, or senior. Every single student in the school fit into exactly one of those categories. Nobody was in two of those categories, and everybody belonged to exactly one of those categories. Right? There was not a student in the school that was not any of them, right? And nobody was both of them. So you had all the students, and you broke them up, and there wasn't anybody that was in two of them, and everybody was in exactly one, and that's a partition. Okay. So freshman, sophomore, junior, senior, it's a great way to remember about a partition. And if there is a partition, then it's going to be either stratified or cluster. If it's not partitioned, then go to the next page. If it's not partitioned, then it will be one of these last two that are wildly different. So you'll be able to instantly detect, oh, it's going to be this one or that. These two, on the other hand, are easy to confuse unless you're careful. So each of them has your sample somehow partitioned. And I had written an example, a terrific example, and I was so proud of myself because I came up with this example before we had COVID. And my example was that there was a contagion spreading, and we work at the airport. We work at the airport. There's a worldwide contagion. And what we're going to do is check incoming passengers for the contagion. Maybe all we got to do is check their temperature. Okay. If they have a fever, then you go over here, get more testing. And if not, off you go. Okay. Are inbound passengers to the airport partitioned in any way?
Yeah, by their seat sometimes.
By the airplane. Nobody inbound to the airport's in two airplanes. Everybody arriving at the airport on a flight is in exactly one airplane. So all of the inbound passengers get partitioned by the airplanes that they're in. If I want to do a stratified sample, then what I would do is I would go to each airplane. I would go to every partition and then once I am at the partition, I would do a random selection. So maybe I would go to every inbound airplane and at random pick like 10 people, check their temperature, and I do that all day long. That would be a stratified sample. It goes every and then it goes random. For cluster, these two words are switched. First is random and then is every. So for a cluster sample, I would randomly select some airplane. Maybe I randomly select 3 airplanes or 2 or 10, but I would randomly select some of the partitions and then check the temperature of every person on the airplane. Okay?
So stratified is like TSA. So you go to your airline, you drop off by your airline, and they randomly select the person to check. You go through security.
Well, you have to ask, are we partitioned when we go through TSA?
So I was just thinking basically like the airport in general, you get dropped off based on your airline.
Okay.
So
you would get partitioned by your gate number or your entry point, like at DFW, I understand.
And then you're going through security at that gate, and then they randomly choose a person to.
If their choice is purely random, then yeah. If you want something that's probably better, I would say the ports of entry to Mexico. Because they are going to check at every port of entry, but it's quite literally random. It's like Have you been there?
They'll randomly just check you.
Yeah. It's like you just keep walking through.
Unless you white. If you white, they just let
It's
you.
like green. No, they have green light, red light. They have a green light and a red light. And if it's red, it's picked at random, and you get searched. Everything gets searched. But if it's green, just cruise on through. No, and it ain't just white people, because they love to catch folks smuggling guns into Mexico.
Oh, you know what the LAPD do? Or cops and
They've been taking guns to Mexico.
Yeah, they confiscate the guns from all the from all the guys that they arrest, and they sell them right back to the cartel, and then the cartel sells them right back.
And it doesn't escape the military down there that happens. So they've either bribed someone or they will get caught, and it will be unpleasant in the Tijuana jail. At any rate,
Not gonna lie, I count up on it.
it's got to be random, or it doesn't truly qualify, right? You go to every partition and then do a random selection. Now, if the TSA, if you really, like right before you're boarded on the plane, I know that they'll come and tell you, oh, you've been selected for random screening, random additional screening. But I'm not convinced that that's always truly random. I mean, it could be.
Stereotype.
It could be, because you hear stories about, like, old grandmas and infants and stuff being part of this. So it could be random, but I feel like it has a bias in it somewhere. If I were choosing the airplanes to look at for my cluster sample, and if I was doing anything at all to have it not be random, like maybe I only wanted to look at airplanes that were not domestic, that's a problem. It has to be genuinely random, right? I would need to know absolutely nothing about the flights, and use like a random number generator to say, okay, it's the first, 10th, and 150th one on the list. And those are the ones I'm going to look at, because those are the ones that like came out of my bingo ball machine, or those are the ones that my random number generator produced. If it starts to talk about random, then it needs to be genuinely random. There can be no influence at all. And neither of these is a random sample, but they both contain this word, random. There's a random component to it. Okay, so if there is a partition, it will be one of these.
So the stratified is just every partition, and then they randomly select from that.
From within the partition.
But cluster is randomly selected partition, but everybody.
Everybody in the partition. Yeah. Yeah. If there is no partition, then it must be one of these last two choices, which are about as different as they could possibly be. You have random, sometimes called simple random, where it's truly, truly random. You could almost think of this one as if the partition was the trivial partition, where everybody belonged to the very same partition, right? Because then you would the stratified samples would say, let's look at every partition. Well, there's just one. And if I'm going to then do a random sample, then the regular random sample is it's not truly stratified, because a partition must not be a trivial partition. There's more than one category. Okay. For a simple random sample, sometimes just called random, there's no partition at all, and it must be genuinely random. You would have to use bingo ball machine, right? Those come out at random. So that's a way for me to pick random numbers, kind of like the lotto machine, where there's a whole bunch of balls blows around, some come out. A random number generator on a computer. These are actually only quasi-random, but it's good enough for taking samples. When was it? I think it was back in the 50s or 60s. There was this book that was printed, and it was It was a book of random numbers. It was like 1 million random digits. Or it could have been 10 million random digits. It had never made one since. And how did they do it? At the time, they didn't have complicated computers. They somehow measured like voltage variations from something like literally like a lava lamp. Like the lava lamp would move around and do its thing, and then that correlated to the voltage in this circuit, and they would just periodically read the voltage off the circuit and then record their number. And that's how they generated those random numbers. There's got to be something that's happening that's truly has no pattern. Okay, and if it's not that, it's convenience. And a surprisingly high number of samples are convenience samples. If at any stage in the sampling process you are unable to adhere to your sampling strategy, it will devolve instantly into a convenience sample. If I'm doing, let's say I'm doing a simple random sample and one of the balls comes out and I'm like, I don't like that one, and I toss it and get the next one. It ain't random anymore. It became convenient, right? If I'm trying to do a cluster sample and I'm on the airplane and I'm checking everybody's temperature and this lady don't want to let me check her temperature, if I can't make her give it to me and I just skip her and go on, it's no longer a cluster sample. Now it's a convenience sample. Because I had to bend, I had to change my strategy in a way that just allowed me to continue to collect data. That's a convenience sample. So there's quite a lot of sampling that's convenient. It's not necessarily bad. It can be very bad. It doesn't have to be very bad. But if it is convenience, and we're like writing a report or something, we need to be forthright with that information. I have seen scientific papers where it says this was a convenient sample. It is okay. But what's not okay is to try and conceal that. Right? So an awful convenient sample would be like, my typical example is, okay, I want to know about job satisfaction at the hospital. Okay, lots of different folks work at the hospital. I'm going to collect my sample like this. I'm going to go to the break room right now and just ask the folks in there, and that's it. I'll write my report from that. That's like totally convenient for me. I didn't have to do any work. On the homework, you might see an example that says, well, this person was picked because they were like, in the first 100 folks on our list. That's convenient. You just happen to appear on the first page, and they just looked down and said, let's call this person. That's convenience. It's not random. Okay? For it to have been random, they would have had to have been chosen at random somehow from this list. But if you got picked just because you were in the first 100, somehow that means maybe we only called the first 100. You were within the first 100. That's how you got picked. Okay?
So say you put that list on a wall and threw a dart on it, that'd be random?
Almost. Dart's not random because you can aim.
Well, close my eyes.
If you close your eyes and threw
Would that be considered random technically?
I think it would be better if it was like you had a handful of darts or a bunch of darts, and you covered your eyes and like all the darts are red, but one of them's yellow, and you throw them, and you don't know which one you threw that was yellow, but then when you're done, you take your blindfold off, and whichever the yellow one was on, well, that's the one you pick. You see what I'm saying? Yeah, I saw a video where Mike Tyson like hit a bullseye with the blindfold on.
No way.
Yeah. A researcher selects every 348th Social Security number, surveys the corresponding person. Is it systematic? Every 348th.
Yeah, that's not
Yeah.
random.
That is their system. I'm starting here at the first one, and how do I pick the next one? I'll go over 348. And then how do I pick the next one? I'll go over 348. That's systematic. that is systematic. A man is selected by the marketing company. He's going to participate in the focus group. He was selected because every 77,500th person was being selected. Is it systematic? Yeah. And this is my strategy for solving these problems. The first thing I'm going to ask is it systematic? Because if not, then the next thing I'd ask, is there a partition? So let me do a similar question on this one. The company says that the woman was selected because her name is among the first 400 in the phone number listings.
That's like that one you said earlier, it was, convenient.
Convenience. Yeah. It's like there's thousands of phone number listings, and why did you get picked? I don't know. Well, I'm just going to call the first 400 on this list, and you were one of them. It was convenience. We want to do satisfaction surveys. We have a database, and the company randomly selects 50 customers and asks them about their level of satisfaction. Okay, it's not.
It's either going to be stratified or clustered.
Is there a partition?
I thought it was random. That was random.
Yeah, the partition is the actual company, isn't it?
So the partition would be the customer, no?
Isn't that the trivial part? How is that different from the trivial partition? So this company has a database of some sorts. Are they going to have a database
That'd
that's
be like the planes, right? The database would essentially be like the plane. And then
well, no, the database would be analogous to all of the passengers that are going to be inbound. Okay, how are they carved up? Does this company really care at all about non-customers? If I go and look at their database, will it be filled up with non-customers? No. They would have to have a database of just everybody for it to be customers and then also non-customers. That would comprise everyone. So it makes sense that the company is only going to have a customer database consisting only in customers. They didn't partition it into like their best customers and their weakest customers. They didn't partition it into current customers and old customers. It's just their customer database. So there's no partition that I can detect. And then they proceed to randomly select 50. If they had partitioned this first into their best customers and worst customers.
And then 50 randomly got selected, then that would be either stratified.
From within each, that would be stratified, yeah. If they partitioned it into best and worst and then only interviewed the best, that would be clustered. Okay? But as it stands here, this is just random. So it has this word that they randomly select, but there's 3 sampling techniques that contain that phrase. So we have to be sure when it's a random sample or when it's clustered or stratified, and you do that by looking for the partition. Here you've got Charlotte. She's divided her day up into 3 parts. Partition. You've got these 3 partitions, morning, afternoon, and evening. She then measures at 4 randomly selected times within each of those partitions. Stratified.
Now it would be clustered if she only took 4 randomly selected times from like the afternoon.
Mm-mm. That would be just something not named. If she said, I'm going to randomly pick the afternoon, and then at every single point in time in the afternoon, she checks her stress level, that would be clustered. So she would have to, at every moment, be checking her stress level. That would probably increase her stress levels, having to do that. So that's cluster. I would say, okay, at random, it's afternoon, and then constantly you're having to check your stress level That's actually probably not even doable. Maybe you could do it every moment, every minute.
Like a monitor on
Yeah. So this is stratified. A woman experienced a tax audit. Tax department claimed she was audited because her name is among the first 300 on the list. Ooh,
it. Says convenience now.
it's convenience.
Right, I thought one said that.
What yours likely said was that
Every 750th person, okay, I got that.
well, if it was every 750th, that'd be systematic, right?
I
Okay.
thought it was the same.
There's another version of this question. What does yours say?
Mine says, a woman's experience with tax audit, the tax department claimed that the woman was audited because she was randomly selected, somehow it was random.
Okay. So there's another version that goes like the tax department claimed the woman was audited because they were auditing all the taxpayers in her tax bracket. All the taxpayers in her tax bracket. Cluster. Because it's partitioned into tax brackets, and you're interviewing everyone in that tax bracket. Here, it's just among the first 300, so it's random. Or convenience, sorry. Market researcher has partitioned all residents of a certain region into categories: unemployed, employed, full-time, employed part-time. She is surveying 60 people from each category.
Partition there.
There is a partition,
All.
stratified. This one's stratified. Because she's got this certain amount from within each partition. Presumably, she's randomly selecting them from within each partition.
Now, if it would have said all of them, then it would have been cluster.
If she is surveying all the people who are employed full-time, cluster. Surveying all the unemployed people, cluster.
So mine is cluster, because she's randomly selecting 4 neighborhoods in a certain region. She is surveying all the people from each neighborhood.
That is cluster, yeah.
Yeah, mine was the same thing. Researcher randomly selected 5 businesses from a certain region, surveyed all employees.
Yep. Okay. The rest of the questions, 12, 13, 14, and 15, have to do with this idea of the frequency table. So finally, we are practically done with the vocabulary. Now, time to look at. There's still some more words that you probably haven't heard of, but those words, I could list them out. They are frequency table, and histogram. And the big idea here, the big takeaway, is that these two things are, this is a table that organizes some observations. This is a picture of that table. They tell you exactly the same thing. If you have a histogram, you can recover the frequency table. If you have a frequency table, you can draw a histogram. A histogram is kind of like a bar chart. And a frequency table is pretty darn fundamental. Over here I make a T-chart. On the left, I have classes. On the right, I have frequencies. So I'm going to define some classes and then make observations of how many times I saw something that happened in that class. So let me consider heights. So height of the people in my sample. Okay, so let's say I looked and I saw that the lowest height that I saw was 55 inches, and the tallest height that I saw was 75 inches, let's say. Okay, I can partition this interval in the following way: 55 up to 60. And let's say I'm always just going to round to the nearest inch, right? Okay. So from 55 to 60, and then 61 to actually this should have been 55 to 59, and then 60 to 64, 65 to 69, and then 70, 74, and then the very last one would have been 75 to 79. Okay. So you can see that if everybody's height gets rounded to the nearest inch, like if you are actually 59.4 inches tall, we'll just say 54. If you're 59.6 inches tall, we'll say you're 60. Everybody will fit into one of these classes, but not two of them. Right? And I look at my collection of people, and I only had one person in this most tallest class, but I had 3 here, and I had 8 here, and then 2, and then also 2. Let me change that. I'll say 1. Okay. That's a frequency table. I have classes, and then this is the quantity of the observations that I saw. This is one person in this class of height. 2 people had heights in this range. 8 of them had heights in this range. Okay. The histogram for this there's 55, there's 60, and all I will do is list the lower limits, they're called. You have your lower limits and your upper limits. So I'll just put out my lower limits here. 55, 60, 65, 70, 75. And I can make what's basically a bar chart where the height of the bar corresponds to the frequency. So that has a height of 1, and this bar has a height of 2, and then this bar would have a height of 8, and then this bar has a height of 3, and then there was just one person in this last class. And I can write the number above each of these bars to indicate to you what the height was. Or I could put the numbers over here on the side. And that one has a height of 8 because it's got the 8 on the y-axis. If you have a histogram, you also have the frequency table. If somebody just gives you this picture, you can write down that table, and vice versa. Okay? We're going to have to make use of this fact to get our work done. If we don't use this property, that these tell you the same thing, then these last four problems can be very challenging, mundane, it can be hard to do just because of the details involved, having to do it by hand. We're going to take advantage of this correspondence because we're going to say, okay, here's this data. We're going to build a histogram out of that data so that we can then write down the frequency table. Otherwise, you would have to look at your data one by one and do something like where you make tick marks, like 1, 2, 3, 4, and then 5, and 6, 7, 8. I'd have to look at each data point and say, which class does it fit in, and then give it another tick mark until I was done looking at all the data points. And you can imagine what a problem that would be if you had, in this case, 45 data points to look at. Now, that's doable by hand, but I already don't want to. If there was 500, it would be really challenging. Think of the likelihood of how you could make a mistake. So we would want to leverage technology wherever we could to eliminate those mistakes. Also, there's going to be this concept that we have to get right with pretty quickly. Regina brought it up earlier. It's about this bell curve. This is actually called the shape of the distribution. Every histogram has a shape to its distribution. The shape of the distribution is the smooth curve that you could draw through the tops of the middle of each bar. Okay? The histogram itself is very jagged. It has these bars. They all have a width of 5 right here, don't they? They all have a width of 5. I know that because 70 minus 65 is 5. 75 minus 70 is 5. 65 minus 60 is 5. And for any classification, this lower limit of the next class minus the lower limit of this class is the class width. It's the difference in two consecutive lower class limits. That's the class width. So this class width is 5. Don't be looking at this and thinking the class width is 4. It's not 59 minus 55, it's 60 minus 55. That's our class width. And it's very jagged and jumpy. The shape of the distribution is a smooth curve. Okay? And this one looks like that bell curve shape because it increases to a maximum and then decreases back to a minimum and is roughly symmetric. So then that means it's called a normal distribution. Normal, that bell curve is truly called a normal distribution. And here we will say just you are approximately normal if, number 1, you are roughly symmetric, and 2, you increase to a maximum before decreasing back down to a minimum. If you satisfy those two things, you're approximately normal. All right, now we can do the rest of the questions. The accompanying data, it's got 45 commute times of workers in Chicago. They want us to construct the frequency table. The class width should be 15. It should begin with a lower class limit of 0. They've got the first number filled out. So that next one right there, next one after it would be 30. And so on. Just keep adding 15. And that's the first thing that we will do always is to fill out the lower class limits because that's the easiest thing to do. $16.
So then, it'd be 0 to 14 then.
Yeah, 0 to 14.
15 to 29.
Yeah. 30 to 44.
45 to 59.
Yeah.
60 to 74. What would we do with 7? Oh, would that be, because technically the next one would be 90, so it'd be 89?
Yeah. Also, all of these have a difference of 15. 44 minus 29 is 15. Okay, so now that we've got all the class limits filled in, we need the frequencies. That would come from this table. Like this person has a commute time of 4, so they would belong to that first class. Could you imagine going to each of these classes and trying to keep track of? It would be a huge pain to have to do that. What we will do is click this little boxes up here in the top right corner. Okay, you click it and you say Open in StatCrunch. We are going to make big use of StatCrunch in this course. Open in StatCrunch. Your StatCrunch window opens, and that data, that data is loaded into the table. Now this looks like Excel. It isn't. It's very different from Excel. It won't work like Excel at all. Okay, but it's reminiscent of it. This column has the name variable 1. That's the VAR1. And if I were to look at this, there would be 45 rows of data. We want to take advantage of the fact that there's a correspondence between the histogram and the frequency table, so we will go over to Graph, Histogram, and click it. Graph, and then Histogram. We're going to tell it where our data is located. It's in the first variable, VAR1. We need to tell it where do our classes start. Here they're calling them bins. Bins, classes, buckets, boxes, containers. It's all the same thing, right? So they're calling them bins. They're going to start at 0. There's a width of 15. The only other thing I want to tell it is value above bar. So that way it'll tell me how tall it is. I don't even have to look. Once I do those 3 things...
You never do nothing else with it?
No, you say compute. All right? So you should be looking at... It should have the following properties. It starts at 0. It lists all the lower class limits. It has the value of how many observations there were in each class at the top of the bar.
So you must have at least one value for select columns.
Yeah. So at the very top, you have to tell it in which column is your data located. It's not smart enough to know that if you only have the one column of data, that's what you meant. See how here I have the VAR1 picked?
That's it? Just click on it. Highlight it.
And when you pick it, it populates it over here.
Somewhere else.
Select columns. Did you pick the VAR1?
Yeah. You go
Okay.
group by, right?
No. You don't pick group by. You go down to bins and put 0 and 15. And value above bar. All right. Well, now I have, now I know what my frequencies are for each classification.
So 0 to 14 is that 5?
For me, it's 5. And then my next class has 16, and my next class has 11, and then 8, and then 4. And there's only one person with a commute time more than 75 minutes. And this is us utilizing that correspondence between the histogram and the frequency table. That's just the first part of this problem. The next thing they're asking is, do the data amounts appear to have a normal distribution?
Well, for the frequency?
What does it mean to have a shape to your distribution? You start off with a histogram, draw a smooth curve through the tops of the middles of each bar. To be approximately normal, you have to be a shape that is roughly symmetric and increases to a maximum before decreasing to a minimum. So this does increase to a maximum and then decrease to a minimum, but it's not symmetric, right?
When you mean symmetric, do you mean it's like one on the left side?
The
of
tall bar should be in the middle,
Oh,
and on either side, there should be about the same thing going on, right? So even if I didn't look at this stuff here in the middle, this one on the left is 5, but this one over here is just 1. To be symmetric, I would expect them to be about the same height. And then these two bars should be about the same height. And then these two bars should be about the same height, right? And as I work my way in from the edges towards the middle, if the bars are about the same height, then that's symmetry. Furthermore, they would have to increase and then decrease, so then that would give us both of them. So this is not symmetric.
So it might be symmetric. Because
Of course not.
versus
And
tall.
then is way lower than the beginning and your height is not the middle.
I think so.
Let me see. So my answer would be no, it's not normal, because while the frequencies start low, proceed to one or two high frequencies, then decrease to a low frequency, the distribution is not symmetric.
Mine's like kind of symmetric, isn't it?
No.
No.
Because of that second bar and the first one being so much taller. In the loosest sense of the word, it would be rough symmetric, but it is not close enough. That is what we'll actually call skewed.
Mine?
Yeah, and mine too. Mine will be skewed to the right, or positively skewed. They may ask us that here in a moment. You can detect skewness because as you draw the shape to the distribution, you can see which side has a tail and which side has the body. So it's like if I carve it down the middle, then the tail is over here, but the body is over here. The tail is on the right, so it's skewed right. Examine the data and identify anything appearing to be unique. Let's look. I see a lot of numbers that end in 0. That's what I see right away. 60, or a lot of numbers that end on the 5, right? It's like folks are rounding a lot. I'm going and I'm interviewing them. I'm saying, "What is your commute time?" And they're like, "Oh, it's 45 minutes, or 15 minutes, 45, 15, 15." And what's the true likelihood that two people's commute time would be 15 on the money? Why isn't it 14? Why isn't that one 14 and 16? How come theirs couldn't have been 11 minutes? What if those was 47 and they just said 45 because they don't feel like, that's just how people work. This person got specific with it, 4. 12. 28. If everyone was being honest with me, they would all be like that. 5 and 0, to end in a 5 or end in a 0 should not be that common. So most of the data values are rounded to the nearest 5 or 10 minutes. And they may be estimates. They might be estimates of the actual commute times. Let's see. Is there any other ones we should check? You're talking about what now? How they might be from 2 different populations. Do we see a gap in the distribution?
Well, what do you mean gap in the distribution? Well, yeah.
Is there a bar, notice how these bars all touch each other. Is there one of these bars that's like 0? No. That would show you a gap. Because let's say that this bar right here was 0, then these folks all live close to home, and these folks live far from, close to home. Everybody lives close to home.
Everyone.
These folks live close to work, and these would live far from work, and that would be 2 different populations.
But they have nobody that lives 45 to 60 minutes away from them. Kind of thing.
Yeah.
That would be
So
the gap.
that would be if there was a gap, if no one was here. Right? But
So
I've
that's
got
what
8
it is.
people there, so there's no gap. The unusually large value of 80 minutes appears to be an error in recording the data. I don't know how that would be true. It doesn't appear that way to me. It's the biggest one, but somebody's got to be the biggest one, you know. Just because it's the biggest one doesn't necessarily mean it's an error. The data are presented as quantitative, but are actually categorical. In the social sciences, they like to use these 2 words, quantitative, categorical, instead of nominal, ordinal, interval, ratio. The reality is that you have the nominal, ordinal, interval, and ratio, where categorical is just nominal. And then all the other ones could be quantitative. Unless it's ordinal but not quantitative, then it's like confusing. They don't have a word for that. So think of categorical as nominal and quantitative as one of the other ones, right? The data are presented as quantitative but are actually categorical. Well, no. Commute times are at the ratio level of measurement. They're definitely not categorical. So it's not any of those other 3. It's just that they all look to be rounded. All right. Now they want us to do basically the same thing again. We have we work in a factory and they make screws. And I'm doing, let's say, a quality control. There's 30 screw lengths. And we have 30 screws that we enter our sample. We want to construct a frequency distribution. So we're going to use a histogram. Begin with this as our lower class limit and have this 0.010 as your class width. So if that one's 1.470, then this one would be,
1.480.
yeah.
So mine's 0.01.
And then I want all of my upper class limits. So if this one's 1.480, how close can I get to 1.480 with a 3 decimal number, with 3 digits after the decimal? Get as close as you can to 1.480, but less.
1.469 or 69
Not 69,
or 79.
79. 479 is 1 less than 480. In fact, all of these upper limits have the same digits as their corresponding lower limit, except the last one changes from a 0 to a 9. So this one is 1.480, that one will be 1.489.
Mine is 0.720, so it'll be 0. I don't know. If it's 0.70, what would mine be?
Your class width,
No, the inches, I guess.
Oh, so like,
so what's your lower class limit?
well, it's just
0.720.
What's your class width?
0.010.
Okay, so your next lower limit is 730, and then 740,
I have
and
that
so
one to the
on.
right of that, like how you put 1.479, what would be mine for 0.720?
Everything will be the same except these would end in a 9.
Oh,
So the
okay.
way I look at it though,
Uh-huh.
like, just for my feeble mind to understand it, is for the other columns, these ones, it's just one less than the other one.
Okay.
That's how I see it, it's just like one less than that.
I get it, but it's just throwing off that zero there. Jason.
That's how I can understand it. Because it's kind of confusing. And then we do the chart thingy.
Mm-hmm. All right, so now I want to do a histogram, so I could find those frequencies. I'll click that button to open the data. Click the icon to view the data. It gives me 30 screw links. Okay. Down here, or over on the right, top right-hand side, you can click those little 2 blue boxes and open in StatCrunch. StatCrunch opens up, and now I will go to graph, histogram. I tell it, right there's my data. Click this one. I'm going to tell it where my containers have to start. They start at 1.470 for me. They have a width of 0.010 and value above bar. It makes my histogram. Puts all those, it looks at the lengths of each of those screws and just makes you the table automatically. We're able to recover what the frequencies were. Because the frequency is the height of the bar. All right. That's it for this question.
Under the bin, you still put the zero, right?
Under the bins, you got to tell it where it starts. That's your lower limit. So for you, it'd be 0.720. And the width is 0.010. Because if each of these bars each of these bars should correspond to one of these rows. So this first row starts at 1.470. That's why that says 1.470. And it contains every possibility between 1.470 but less than 1.480. As soon as it's 1.480, it'll be in the next class. All right, so on that one, it's just making the table. 14 and 15 are really easy, but they look weird. There's a high likelihood that they could confuse you. So in 14, they want to talk to you about a relative frequency. Relative frequency, very easy. Looking here at my frequency table from earlier, how many people were in my sample here? Well, I can look at my frequencies. There was 1 and then another 2, so that's 3, plus 8, 11, 12, 13, 14, and then plus 1 is 15. 15 observations in total. I can make another column that is the relative frequency, which is it would just be fractions or percentages. I'll say 1 out of 15 and 2 out of 15, 8 out of 15, 3 out of 15, and 1 out of 15. I could take each of those fractions, turn it into a percentage, right? could. Also, it's clear that this should add up to 1 because it will add up to 15 over 15, which is the number 1. And 100% is the number 1. So no matter what way you look at it, fractions, percentages, it's going to add up to 100%. It's the relative frequency. It tells you what proportion 8/15ths of these people were in this height category. Okay? So on the assignment, they've given you, if you click the thing to view these frequency distributions, they've given you 2 frequency tables. Okay? One of them for non-filtered cigarettes, one of them for filtered cigarettes. Look at how the classes don't match. They overlap some, like this one has 10 to 13, and 10 to 13 doesn't show up until down here. And 14 to 17, 14 to 17, so the class width is the same. But it would be easier for me to figure out what's going on here if all of the classes were identical. So what I will do is make a new table that has all of the classes, 2 to 5 and 6 to 9 and 10 to 13 and 14 to 17, and then 18 to 21, and then 22 to 25, and 26 to 29. That's all of the different classes used by either table. See what I'm saying? Like this one has all of the high classifications because they're non-filtered cigarettes. Naturally, it's going to have the higher tar. This one has the low classes because they are filtered, so that's where it'll have the lower tar. And then I want to make a relative frequency table that has 2 columns, one for non-filtered and one for filtered. Okay? For the non-filtered cigarettes, there is a total of the frequency series of 25. If you add those numbers up, you will get 25. Same thing over here. There's 25. Okay? So, in the class of 2 to 5 milligrams of tar, we had an observation of 0 non-filtered cigarettes in that class. 0 out of 25 are 0 out of 25 non-filtered cigarettes have this much tar. None of them. I mean, I can list all the classes. I can list classes from here to infinity, and all of the frequencies would just be 0 afterwards because there was no observations there. Okay, so if I glue on another class, I can always just glue on another class and stick a 0 for the frequency. Nothing wrong with that. In the class of 6 to 9, looking at just the non-filtered, I would also have 0 out of 25. But in 10 to 13, it would be 1 out of 25 because that right there is a 1. And I would just keep going. In the next class, it would be 0 of 25, and then, 13 out of 25, and then 6 out of 25, and then 5.
We're going to put percentage on the red.
We'll do that in a minute.
What's up? I like it.
For the filtered, I would have 3 out of 25, and then 1 out of 25, and then 6 out of 25, and then 15 out of 25, but then it's just 0, 0, 0 after that because there's no observations there. Now that I have made myself a new table from their frequency table, right? This is a relative frequency table. These are all fractions, right? It's exactly the numbers from the frequency table, just over 25. with some extra zeros. These two zeros weren't there before. They're there now because there was no observations there. These three zeros weren't there before. But they're there now because there was no observations there. And if something is over 25, and I would like it to look like it's over 100 so I can read it as a percentage, why don't you just multiply by 4/4 instead of running it through your calculator constantly, because it's a lot faster. I could beat you in a calculator race. 1/25 is 4%. Multiply by 4/4. 13/25, that's 52%. 6/25, 24%, and so on. I'm just multiply the numerator by 4, multiply the denominator by 4. For example, 6/25 times 1 is 24/100, which is exactly 24%. See what I'm doing?
So 2/25 would be
8%. All right. So I can now fill out all these percentages. There is no way to get this
So
problem.
basically, you just do the numerator times 4, and you get the percentage.
That's what it boils down to, because once that denominator becomes 100, you are just looking at the numerator to capture what the percentage is. Because to divide by 100 means the percent symbols. So the writing 24 divided by 100 literally means 24%.
No. It's stuck on my chart somewhere.
How's that?
Because I was trying to figure this out, but then I have like the tar in milligrams. I have 4, 7, 28, 31 at the end, and then I went to that frequency distributions, and then I put in the numbers. So where are you getting the 25%, like the whole number?
Okay. I counted how many observations there were. 1 plus 13, 1 plus 0 plus 13 plus 6 plus 5 adds up to 25.
Okay.
3 plus 1 plus 6 plus 15 adds up to 25. Okay? That's what you got to do. You got to add up all of the observations that you had, and we're going to go through each class and just divide by that total. And then I could say that for the class of 18 to 21, I had 52% of them. 52% of the non-filtered cigarettes fell into that class. 24% fell into the next class, and 20% in that class. And 12, and 4, and 24, and 60. And naturally, these percentages need to add up to 100%. I mean, 60 and 24 and 4 and 12 had better add up to 100, or I made a mistake. It does, right? These three add up to 40, 60 and 40 is 100. Then they ask you if, does it appear that cigarette filters are effective? Well, unfortunately, yes. It appears that they are effective at reducing the milligrams of tar that you are able to measure with your little machine. Clearly doesn't make them safe. It just makes them, I mean, the cigarettes that had a filter are in the lower classes. They don't have any in the higher classes, right? But the ones without a filter, they're all down here in the high classes. So, yeah, they do reduce tar. In the last question,
Does this one want fractions? Does this one want fractions?
on this one, no. This one wants you to accumulate the frequency, which is why it has this word cumulative. So if I look at these classes, they're not genuinely classes anymore because they all overlap, right? If something is less than 60, it is also less than 70,
Right.
right? So to be less than 40, that would only be this first row. Those are the only ones that are less than 40. So I'm going to put 3 for this one. But to be less than 45, you would be either the second row or the first row. So you'd add it. So the next one would be 5. And then this one I would just add, I would just take the next class. In my third class, I had 5, and I would add that to the previous quantity each time. So that way you accumulate up to the maximum.